It's been a very interesting evening. The intent today is to review inverse functions. We begin with a warm-up. I'm just going to leave it as written and describe it. Jay's shipment business is described by the demand function P at x is equal to negative x plus 5.4. This is a linear relationship that's in thousands of shipments when you consider the letter x. The cost function is represented by another linear function, C at x is equal to 8x minus 15. C at x is also in thousands of dollars. Determine the maximum profit that Jay can make. When I see the word maximum, I think vertex. Vertex reminds me of parabola, and I should be concerned with the letters H, K. This is a profit question, so we have to remember the formula. Profit is revenue minus cost, and that makes sense. You have to take away the money you spend when you're trying to make a product and earn some revenue. So we take the demand function, we multiply it by our shipments, and we subtract the cost function. So that means we have to substitute in negative x plus 5.4 and multiply it by x. And then we have to subtract our expenses, our costs. So that's represented by the function C at x. Simplifying and expanding this expression gives us a polynomial. Don't forget that when you expand, it's really important that you manage your signs carefully. A negative times a negative gives us positive 15, for example. Remember, the negative x is only affecting the x, not the 5.4. When we decide it's time to convert our standard form of our equation to vertex form, we start by bracketing the first two terms and factoring out negative 1. Dividing each term by negative 1 gives us positive x squared minus 2.6x. Now we prepare for our perfect square trinomial. So we have to apply the trick, b over 2 squared. So negative 2.6 over 2 all squared is 1.69. Think 13 times 13, 169. So we add and subtract the quantity to create the perfect square trinomial, and then we move it out of the bracket, leaving us a trinomial and a simplification. When we look at our trinomial, we take the square root of the first term, the square root of the last term, and borrow the sign from the middle term. We've now got a perfect square. Simplifying the last two terms gives us 16.69 as the k value of the vertex. So the maximum profit occurs when your shipments are 1,300 shipments, making a profit of $16,690. So now we're moving ahead to inverse functions. We've seen inverse functions when we apply sine, cosine, and tan. When we have a decimal value, we use the inverse or the opposite of sine inverse, to calculate the angle that generated the value. Let's look at the first example. We've got a linear relationship and we need to sub in negative 18 for y. In order to isolate for the x, I need to move the 2 to the opposite side. In other words, subtract 2 from both sides. Giving me in order to isolate for my x, I have to divide by negative 5. Resulting in 4. So if I analyze the operation steps that I took to isolate my x, I notice that I subtracted 2 from both sides, and then I divided by negative 5. I don't like the way that turned out. Sorry, I'm really having a notation problem here. Better, but not great. So when we moved downward, we applied these operation manipulations. And they appear on both sides of our equal sign because we have what we do to one side, we do to another. Now, if we want to move in the inverse direction, what we would do is the opposite operation. So moving in the opposite direction means we would have to multiply by negative 5 and add positive 2. Let's try it. So if I multiply both sides by negative 5, I get negative 20 is negative 5x. And if I add 2 to both sides, then I get negative 18 equals 5x plus 2. And I'm right back where I started from. So doing the inverse or opposite steps led me back to where I started from. So if I were to ask you to rewrite the function f at x equals negative 5 plus 2 as an inverse function, I would consider my operation steps. So when I look at f at x, I take my x and I multiply by negative 5. And I add 2. So that means when I move in the opposite direction, I should subtract 2 and then divide by negative 5, giving me the inverse function. And that means that I would write my function as f at x equals negative 5x plus 2, while my inverse function would be x minus 2 divided by negative 5. Let's try it with g at x. So I start with my x, and I notice that I multiply by 2 first, followed by subtracting 4. So if I move in the opposite direction, then I am applying add 4, divide by 2, giving me the result g at x is equal to 2x minus 4, while the inverse of g at x is x plus 4 divided by 2. Let's take a look at what these equations look like. So when we looked at g at x, we had 2x minus 4. This is a linear relationship, so let's plot it. Negative 4. I'm rising 2 over 1. So I rise 2, I move over 1. I rise 2, I move over 1, and so on. So I plot my line, which is 2x minus 4. When I calculate the inverse, we calculated it as g at x equals x plus 4 over 2. So if we were to plot the inverse function of g at x, we have to break it into 2 component parts. We divide the first term by 2 and the second term by 2, giving us 1/2 x plus 2. Plotting this relationship means we start at the b value of 2, we rise 1, and we run 2. We rise 1, run 2, rise 1, run 2, and so on. We connect the lines and we form the blue relation. Let's label it. Okay. So observe that if you consider the line y equals x, in other words, 1, 1, 2, 2, 3, 3, negative 4, 4, negative 7, 7. So when you look at this y equals x line, you notice that the function and its inverse are mirror images. In other words, y equals x is the fold line. So imagine you bend your paper along the dotted line. You would notice that the equations, the linear equations, line up. So we've seen one way to determine inverse functions is to identify the original function operations and then do those operations exactly in reverse order and opposite operation. We've seen that there is a reflection, and the y equals x line is considered the fold line. So another way to consider inverses is if we look at the point AB on our graph, then BA is considered the inverse coordinate. So what are the implications for domain and range? So if f at x is the original function, we would describe the x as our domain and the y as our range. If we're considering the inverse function, then the range becomes our x values, the domain, our y values. Let's go back and take a look at the curve we just generated. So if I look at this coordinate, 1, 2, 3, 4, so that would be -4, 0. And I consider reversing the digits. And so now I have 0, -4. Then I'm going to map out my new coordinate on the inverse line. If I consider the coordinate 0, 2 on my inverse function, it's related to my original coordinate and identified as 2, 0. They intersect, and so when we inverse or reverse the digits, no change. If I consider the point six, eight, then I predict there will be another point on my graph at 8, 6. Let's see if this is true. One, 2, 3, 4, 5, 6. And in fact, it's true. So we observe that the coordinates in my function, if they're represented by AB, become BA if I consider the inverse function. So if the original function is linear, its inverse will always be linear. Is there an example where this isn't true? Well, I'm thinking of the x-axis. And I'm thinking that it's represented by the equation y equals 0. So f at x equals 0. Unfortunately, when we try to describe its inverse, we're mapping out the y-axis, which is undefined. So this might be something to consider. What is the inverse result? Because if you divide by 0 or manipulate by 0, you get an undefined function. So, food for thought. Let's consider a quadratic function. And let's call it f at x. If we reflect our parabola in the line y equals x, then we're going to identify its inverse. Let's do that. The coordinate remains the same along the y equals x line, and I know that my position is the inverse or the reverse of my coordinates a and b. So I can map out approximately my new parabola. And let's label it f inverse at x. So unfortunately, our function has become a non-function. If we wish to keep it as a function, so should we choose to map into a function, then we have to add a restriction on the domain or range. So if I were to ask you to find the inverse function of f at x, I'm asking for a function. So you might say your restriction has to be y is greater than and equal to 0. Or you could say y has to be less than or equal to 0. So restrictions ensure that we maintain the function property that we may require under in the circumstances we find ourselves. Let's revisit the examples y equals, well, the linear relationships f and g at x. So there's an easier way than thinking about the operations to generate the inverse functions. If we simply switch the x and y values, so f at x is my original function, or the given, we convert it to a y value, and then we flip the x and y, and we isolate for our y. I paused for a moment because I don't actually like the negative. I could leave it as x minus 2 divided by negative 5 if I wished. So you have some choices here when you're isolating for your variable y. Now let's try the right side. So we successfully isolated for our y value, but we need to remember that this is the inverse of my original equation. So we're going to replace our y with f at negative 1x. Same with the right side. Our y is not actually the y we started with, so we replace it with the inverse notation. And so you notice that that's exactly what we generated in our first examples. Let's take a look at the inverse of an integer relationship. So we have a series of dots on our grid. Obtain the graph of the inverse and determine if it's a function. So currently we have a function. So can you please plot the inverse? So we'll start off as an example. -3, 1. So we know we're going to map out 1, -3. Our second point is -2, -1, -2, +1. So we're going to map out +1, -2, -1, 1. So we have 1, -1. Finish the graph. Is it a function? No, because clearly it fails the vertical line test along x equals 1. In our second example, we're given a graph and you're asked to plot its inverse. So I usually look at the intercepts and plot their inverses. Connecting the 2 points gives us our new graph. So we started with f at x and ended with its inverse, f inverse at x. Don't forget to label your x and y axes. We observe that there is a reflection in the line y equals x. Let's apply these principles in the following examples. So we're looking at the value x equals -4 as communicated by function notation. So I'm going to substitute in my equation -4. And I get the result -7. So at f -4, my function value is -7. When I look at question B, I'm able to look at the same equation, and I simply substitute my x's value 5 and obtain 11. So I know I'm standing at the coordinate 5, 11. When we look at question C, we're being asked to subtract our two values. Well, fortunately, we've already calculated them separately. So we know f at 5 is 11, and we know f at -4 is -7, giving us positive 18. In question number D, we're now asked to find the inverse. So let's use our reverse strategy. So our equation is y equals 2x plus 1. So we converted from f at x to y. The next thing we do is flip the x and y values. And we continue to isolate for the y. So when we substitute in for our x, we have the answer. I'm going to keep it simple. So now we're ready to substitute in for -4. I actually made an error. I have a sign, oops. I have to fix this. So I have, in fact, x minus 1 divided by 2. It's the same thing, but I prefer this notation. Just want to make sure I'm okay. It's late. I'm tired. Let's keep going. So in my next equation, I should put in my subtract in this position. So I notice it should be -5. Yeah, I'm happy with that. Okay, lastly, let's look at substituting into our inverse equation at 5. So I'm going to use the y value as f inverse at 5 is equal to x over 2 minus 1/2. We'll try this version. So 5/2 minus 1/2 is 4 over 2, giving us 2. So in step 1, we replace f at x with with y. And in step 2, we switch x and y. I want to do one more example because I'm not sure if it was clear in the last example. So let's make something up. (3x minus 8). So in the procedure, we saw our y becomes 3x minus 8. We switch our x and our y's. And then we proceed to isolate for the new y. And so this becomes negative 3y is equal to negative x minus 8. I'm going to divide by negative 3, and negative 3, giving me y equals 1/3 x plus 8/3. Now I could rewrite the equation as y equals x plus 8 all divided by 3. Let's see if this works in terms of our mathematical operations. So when I move down, my x was multiplied by 3, and then 8 was subtracted, giving me 3x minus 8. So if I move in the opposite direction, I have to add my 8, and I have to divide by my 3. And let's see if that in fact gave us our inverse function. And so we observe that we added 8 and we divided by 3. So we know it's correct. So let's apply the appropriate function terminology. Up there, I've just lost my pen. So now we can say f at x does in fact, and it's the inverse function, equal x plus 8 divided by 3, or we could report it as individual fractions, x over 3 plus 8 over 3. Notice at no point are there any decimals. So if we're asked to find f at negative x, the inverse of x, and we're going to have negative, let's go 4, then we would choose which version we want. I personally like the second one, and so I would substitute in my negative 4 in the x position. So 8 minus 4 is 4, giving me 4/3. So using the inverse function at the position negative 4, that tells me that I'm in position 1 1/3. How useful is this? Well, like I said, if we can consider conversion operations. So if I apply some math in the forward direction and I'm in Canadian currency, So if I want to move from US currency back to where I started from Canadian currency, then I would apply my steps in the opposite direction. So there's a currency implication here. So it's just a way of keeping track of your operations. I hope this has helped explain inverse functions.